This is Marina Bay Sands, one of the most complicated engineering projects ever built. The entire resort stands on reclaimed land containing deep layers of marine clay. Engineers had to construct 3 55-story towers, connect them with a 7,000-ton SkyPark nearly 200 meters above the ground, and then place a swimming pool on top of it holding 1.4 million liters of water. Today, we're breaking down exactly how engineers built Marina Bay Sands, the real problems they faced, and the solutions that made it possible. Because at every stage of construction, from the foundations to the SkyPark, a small miscalculation and the entire project would become a disaster.
We get stuck.
In 2004, Singapore lifted the decades-long ban on casinos and built something the world had never seen. The goal was simple: put Singapore on the global map and compete with the biggest cities on Earth. Las Vegas Sands won the bid. Architect Moshe Safdie got the job. The construction of the building masterpiece began in 2006, and from day one, nothing went according to plan. Let's start with the ground itself, because before engineers could build upward, they had to solve a problem underneath their feet. The entire Marina Bay area did not exist 40 years ago. It was reclaimed from the sea, specifically built up for city expansion. That sounds fine until you realize what reclaimed land is made of. The resort sits on 15.5 hectares of reclaimed land, composed of deep layers of sand and marine clay. Marine clay is one of the worst materials you can build a skyscraper on. It compresses under load, it shifts and absorbs water, and loses strength over time. So, engineers from Arup, the firm responsible for the entire structural design, could not simply dig and pour concrete, because it could turn into a completely failure. So before a single tower could rise into the skyline, engineers first had to create an artificial foundation capable of supporting billions of dollars worth of steel and concrete. Engineers reinforced the base with 5 massive concrete cofferdams and steel diaphragm walls. Then large board piles, ranging from 1 to 3 meters in diameter, were driven deep into the ground, alongside barrettes, to carry the tower's immense weight. These board piles go down over 50 meters, with the largest reaching 2.8 meters in diameter. That is a pile wider than a standard car is long, buried the depth of a 15-story building, just to create a stable base. And there was another problem underground that most people never talk about. The team had to bore through the marine clay to make room for underground car parks and railway tunnels that run directly beneath the facility. They were building on soft reclaimed land, sinking massive piles into it, while simultaneously avoiding active tunnels running under the site. One miscalculation, and they were not just dealing with a structural problem, but they were dealing with a collapsed transit line in one of the world's busiest cities. When the foundation was solved, now it was time for the towers. And here is where the design itself becomes the engineering problem. Each of the 3 towers is broader at the base and narrows as it rises. Within each tower, the legs are asymmetric, 2 straight legs paired with a curved eastern leg that leans against the others. From a distance, it looks elegant, but during construction, it was a nightmare. When you build a straight vertical column, gravity works with you. But when you build a curved, leaning column, gravity works against you, constantly pulling the structure in the wrong direction before it is complete. Substantial temporary support structures had to be built to hold each leg in position during construction, and real-time monitoring was required continuously to assess and analyze the structure as it was being erected. Every floor had to be poured, set, and verified before the next one could begin. Each tower was built at a rate of 1 floor every 4 days. Across 3 towers, each 55 stories tall, that is a construction operation running simultaneously on 3 separate leaning structures, all being monitored in real time, all converging toward a single point at the top, where they would eventually be connected by something that had never been built before. And that something is the SkyPark. The SkyPark sits 200 meters above ground. It is 38 meters wide and 340 meters long, equivalent to 4.5 Airbus A380 aircraft placed end to end. It bridges all 3 towers. But the real engineering challenge is not the span between the towers. It is what happens beyond the last tower. The SkyPark cantilevers 65 meters beyond the end tower, making it one of the world's longest habitable cantilevers. To put that in perspective, 65 meters of structure extends into open air with nothing underneath it. No column and no support, just steel and physics. The entire 7,000-ton SkyPark structure was fabricated in 14 steel segments off-site, then lifted into position using strand jacking. a precision hoisting method that uses tension steel cables to gradually raise extremely heavy components. Each lift operation took over 16 hours and required millimeter-scale alignment to match the complex rooftop geometry. But even after the SkyPark was installed, engineers faced another problem. Once it was up, engineers had to deal with the fact that 3 separate towers do not move identically. Wind hits them at different angles. Temperature changes cause thermal expansion at different rates. The ground beneath each tower settles slightly differently over time. So engineers came with a solution. Because the towers settle at different rates and sway due to wind, 4 movement joints with a range of 500 millimeters were integrated into the SkyPark structure. The SkyPark is not rigidly locked to the towers. It is designed to float slightly above them, connected but allowed to move, so that no single tower's movement tears the whole structure apart. And then, engineers decided to place something even heavier on top of it. A 150-meter infinity pool suspended nearly 200 meters above the city. The infinity pool measures 150 meters long, 8 meters wide, and 1.2 meters deep. It holds 1.4 million liters of water. When filled, the total weight of the pool is 3.6 million pounds. That's over 1,600 metric tons of water sitting high above the ground on a structure that already extends beyond the edge of the tower. The pool itself could not be poured as a simple concrete shell. It was built using 422,000 pounds of prefabricated stainless steel and finished with 254,000 ceramic tiles, adhered directly to the steel shell. The structural bridges connecting each tower were installed with a deliberate 3-inch camber, a slight upward pitch built into the structure, specifically to account for the deflection that would occur once the pool was filled with water. Engineers knew the structure would bend slightly under the enormous weight of the water, so they intentionally built portions of it with a slight upward curve. Once the pool was filled, the load pushed the structure down into the exact position engineers had predicted years earlier. At nearly 340 meters in length, the SkyPark also expands and contracts with temperature changes throughout the day. Engineers used sliding and elastomeric bearings to accommodate this thermal movement while maintaining structural integrity. The entire project, from the first design sketch to the day Marina Bay Sands opened, took just 4 years. Construction began in 2006 and was fully completed by 2010, at a total cost of approximately $6.88 billion, making it the most expensive standalone casino complex ever built. Marina Bay Sands was declared by Las Vegas Sands Corporation as one of the most challenging construction projects in the world. Looking at what actually went into building it, that is not marketing. That is a statement of fact.